In this video, I'm going to demonstrate recording with the Audacity software. I'm going to make a record of the lowest note on the guitar and the highest note as well. Then I'll use the waveform to calculate the frequencies of these notes. So, if you don't have Audacity, you can find it. Just go to google.com and search for Audacity. This site here, audacityteam.org, offers a free download of their open source music recording software. The download links are here. So what I'm going to do is I'm going to start up the program. So in the Audacity program, the first thing you'll want to check is your audio setup to make sure that you're recording from the device that you want to record from. In my case, I'm just going to record from my MacBook Pro microphone. And as soon as I click the red circle, that'll start a recording right away. Okay, so first I'm going to play the very lowest note that a guitar can play. That's going to be with the thickest string, and I want to just not hold any frets down to get the very lowest tone. Okay, let's try it. Alright, that'll do it for my two samples. Okay, so here I did a little bit of talking. Okay, let's try it. And after that was my lowest note. Shortly after that, I fumbled with the strings a little bit. And then I played the highest note that I could play on that guitar. Then I talked some more. Alright, that'll do it. Okay, so we want to zoom in on the waveform so that we can see the actual oscillation of the recording. We want to zoom in with the magnifying glass here. That's a horizontal zoom in this program. And there we can see a good pattern of oscillation. If you need to, you can also zoom vertically by hitting Control on Mac and then clicking. So in Mac you have to hold Control and then click on the vertical axis. It's important though that you do click in the middle if you want to zoom to the middle. If you want to zoom to some other value, you could click up here, but as we'll see, that's gonna not be ideal. It takes a little practice to get used to the system, but there we go. We can see the waveform fills the vertical axis, so that's good. And we can zoom in some more horizontally if we want. What we're looking for here is a clear repeating pattern. And sometimes it can be difficult to tell what the fundamental oscillation of the sample is. So, in this case, we see if we start here and go to here, that appears to be one full cycle of the fundamental tone. If we click here and go to there, that appears to be two full cycles. Now it is possible that I could be wrong in my assessment. There's a lot of trial and error that has to go into this kind of thing. And we'll be able to use a lot of different evidence like FFT, fast Fourier transform diagrams, to help us get a good sense of what the fundamental here really is. However, if I really think that this is the start and end of a full cycle, what I should do is look at the bottom here for the selection start and the selection end. Now this is a time relative to the start of the timeline. So the start of the timeline occurred way back here at the beginning, where I said some words about getting started. So as you can see, 4 seconds went by or so before I even played my first note. So when I make a selection here, that selection is telling me relative to the start of the clock where I'm beginning my selection. You then hold Shift and click again to make the end of your selection. So as you can see, the start of my selection isn't changing, but the end is. If we subtract the end of the selection and the start of the selection, we can get the elapsed time of this blue section here. So what I'll do is I'm going to use 2 fingers on the Mac trackpad here to zoom in. And let's just try to get one typical cycle. According to the selection down here, if we subtract those two, we'll find that 432 milliseconds minus 426 milliseconds is just 6 milliseconds. Let's write that down, because that is the period of oscillation for this note. At least that's what I think it is. Alright, so now that we have the period of the waveform, in order to find the frequency of it, we can just use the formula that the frequency is 1 over the period. So that should be 1 over 0.006. It's 167 hertz. So just to have a little more confidence in that answer, let's go back to Audacity. What we can view is a fast Fourier transform graph. You have to hit Analyze in the menu and then click Plot Spectrum. So in the Audacity menu, click Analyze and then Plot Spectrum. At first, it's going to say that there's not enough data selected because you need much more than just a single cycle in order for this graph to be created. So let's go back and select a little bit more. Okay, so I'm taking quite a large section of the note. Looking at the waveform shows us that the amplitude of it is changing. It's decaying as time goes on. But we also know from our past studies that even though amplitude may readily change for an instrument, it's common for the pitch to stay the same. We could check that, of course, by selecting a new cycle here toward the end of the note. So later on we see that the shape of the waveform has changed a bit. We could still, though, select a single oscillation and check its period to make sure that it hasn't changed much from what it was. If we subtract 5.718 minus 5.712, we would still get 0.006 seconds for the period. So the period really hasn't changed, and that means the frequency hasn't changed either. So let's now select a large portion of the wave, and we'll try to create the FFT diagram for it. So click Analyze and then Plot Spectrum. So here's one version of the frequency content diagram. You could actually get several different versions of it by clicking on this and changing the size from 1024 to 2048, and you just get a little bit different look each time. Okay, what we're looking for is the lowest frequency that appears. So now the axes of this diagram are that they have the frequencies on the horizontal, with the lowest audible frequency being about 20 hertz and the highest audible frequency being 20,000 hertz. And what we're looking for is the leftmost peak, the lowest possible peak that we see. And the volume in decibels is our y-axis here. Now, this program will automatically snap to where it believes the frequency peaks are. So it looks like it thinks there's a peak at 158 hertz. It also believes there's one at 493 and 731. Now 158 was somewhat close to what I had calculated. I had calculated about 167, and the program's calculating 158. So those are pretty close. We could try a different version of the diagram here. So let's see. This time the largest peak, it says, occurs at 162 hertz. The next one would be 247 hertz. These other peaks that come after the fundamental, they're higher pitched harmonics that play a part in giving the sound character. But what we're really interested in at this time is the fundamental. Now it might look like maybe there's another lower fundamental in this case at 77 hertz. And so that one is a lower volume than the 162. And in fact, we can look up what the frequency of the low note on a guitar should be just for further confirmation. So on Google, we could type in frequency of a low E on acoustic guitar. It says that the lowest note on a guitar is supposed to be 83 hertz. So actually, this 77 probably is the fundamental. We don't see it in this diagram, and we don't see it in this diagram, but with the larger size, the 2048, we do start to see it. And then with the 4096, here we see there is a fairly substantial peak there at 81. So what that means is that when I had made my calculation, I didn't really capture the very lowest oscillation. I was capturing the next harmonic instead of the fundamental. Now, how could I ever know that just by looking at the waveform? Well, you could look to see that there appears to be a structure to this wave that repeats itself. There's kind of a double peak here, and then the next peak is just a single peak. Then we have another double, and then a single, and then a double, and a single. So really, the full oscillation is probably supposed to be this, because that's where the pattern really repeats. So the fact that there's a periodicity to this picture which is fundamentally larger in size than just from, say, here to here, that implies to me that there really could be an underlying low frequency oscillation that we should focus on. So, to get the true period, I'll go from this point to that point. And we can see that the period is going to be actually 4.492 minus 4.480. That makes a period of 0.012 seconds. And the frequency would then be 83.5 hertz. Now, you shouldn't just analyze one spot in the note. In order to make a good judgment call, you could look farther along in time to see if you could spot that low frequency oscillation. I think here it's probably clearer than before that the pattern repeats, starting with a low peak and then a high peak, and then a low peak and then a high peak, and a low peak and a high peak, and a low peak and a high peak. That looks like about 4 oscillations of the very lowest frequency. So we can get better results for our period if we use a larger sample. So let's say that I call this 4 cycles, and then I look at the time that it took and do my calculation based on that. Okay, so this is the start, which the program says occurred at 5.851 seconds after the beginning of the recording. Then here's the end, 5.900 seconds after the start of the recording. I'm claiming that there are 4 complete cycles in this region. If we zoom in, we can see where the pattern repeats itself. So now what I would do to get a little bit more accurate value for my period of my wave is I would let the period be the total time divided by the number of cycles. So that's going to be 5.900 minus 5.851 over 4 cycles. Let's see what that gives us. .01225. Now I'll calculate the frequency by doing 1 over that. .6 hertz. And the accepted value was around 83 hertz. Okay, so we could do a percent error here. The percent error formula says you subtract your experimental value minus the accepted, and then we divide by the accepted. And it's common to put an absolute value around this and multiply by 100% to change it into percent form. So we would have 81.6 minus 83 over 83 times 100. .7%. Not bad. Okay, so now let's check the frequency of the highest note that I had played. Here's my highest note. We'll want to zoom in here because the period is obviously quite a bit smaller. So there's a clear pattern here, and if we were just looking for a single oscillation, it seems reasonable that this would be one oscillation. However, as we saw in the previous note, we can't always assume that that's the case. We want to do just a little bit more investigation to make sure that we're especially not off by a multiple of 2, for example. So let's see, this period is very short. It's only 1 millisecond according to the computer. However, this period is so small that it's possible that there could be quite a bit of error there. It may be that there's more digits that would be significant that are cut off here. So I don't think I'm going to go with just 1 millisecond. Instead, what I'll do is I'll take several, and then I could go off that instead. So there's 4 cycles, and it looks like it takes 0.004 seconds. Even that is not great. I might want to go with many more oscillations than just 4. Let's try 8, and then perhaps 16. So there's 12, and 16 there. So 16 oscillations. Let me count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, 16 oscillations. Okay, so here we have what I believe to be 16 full cycles. And like I said, I could be wrong about that. I might be judging it with the wrong idea in mind. Maybe these are actually 32 cycles and I don't realize it. However, if it is 16 cycles, then we're going to want that the period will be given by total time over the number of cycles. So that's going to be this, 12.138, minus this, 12.122, then we'll divide by 16 cycles. It looks like it is 0.001 seconds. And now we can calculate the frequency of that note. It's going to be 1,000 hertz. Let's look up the accepted value for a high C on an acoustic guitar. The accepted frequency for the C that I played was 1047 hertz. So I was pretty close. Let's see what percent error that is. Once again, I'll do the experimental minus accepted divided by accepted. And then we'll multiply by 100%. .5% error. So there was a little more error in this one.